Hello, welcome to the first vodcast of Biology 12. There will be some of these throughout the semester in order to give you kind of a preview of the knowledge before we decide that we're going to do an activity. So first we're going to start by reviewing the chemistry basics so that we have a common language and an understanding in order to relate this to the molecules that function and are required for life. So what I'd first like to do is break down the structure of the atom. So all the elements in the periodic table are found as atoms. A definition for an atom is the smallest part of an element that displays the properties of that element. And so atoms can be broken down into subatomic particles. So that's what I want to look at with you first, are the three subatomic particles. Now, there are three subatomic particles. The first one are the protons. Or not the first one, but one of them are protons. Another one is, or are, neutrons. And the third one, electrons. So they can all be seen, these colored circles that are found on in this diagram. The protons and neutrons, these are the ones that are found inside the nucleus. So they're inside the nucleus. And that's diagrammed right here. So these red and blue are protons and neutrons. The next type of subatomic particle are the electrons. Now the electrons are found outside of the nucleus. So they are found out of nucleus. They are found rotating around in orbits or shells around the nucleus. We'll talk a little bit more about that in octets a little bit later, but they are found moving around the outside of the nucleus in orbits or shells. Now the next thing I just want to do is break down for you is just to remind you that all these subatomic particles contain different charges. So protons, each proton carries a positive charge. Each neutron is neutral charged, hence the name neutron. It has no charge, and electrons are negatively charged. Now it's the combination of these protons and electrons that give atoms a charge, which is next we're going to come to, is the definition of an ion. So one more definition I just want to review with you from your chemistry are ions. And so in atoms we had equal amounts of protons and equal amounts of electrons. So what happens when you might get a sharing or you might get a transfer of electrons is that the atom takes on a charge. And when it takes on a charge, we call it an ion. So ions are atoms that have gained or lost electrons. So usually these have a little positive, a superscript of a positive or negative beside them. Some examples of ones that we're going to come across. So examples are sodium, very important in our nervous system, along with the potassium. Additionally, for example, chlorine and calcium. So you can see all of these have superscripts above them that are showing you the charge on that ion. So these are atoms that have gained or lost electrons. So when those atoms gain or lose electrons, what those two atoms are doing is that they're forming a bond together. There's two types of bonds that I want to draw your attention to, and then I'll break down one of the types into a few subtypes. So the first type of bond is an ionic bond. So this involves, and here's the key word, a transfer of electrons. And this is a transfer of electrons usually from a positive ion to a negative ion. So I'm just going to remind you as I'm writing this down that you should also be writing some notes down unless this is complete review for you. So here's an example of ionic bonding. So here we have a sodium atom. So you can see under here it's saying sodium atom. And you can see it has this one valence electron here in its outermost shell. So it's unstable at this point, and it would really like to get rid of that one valence electron. Well, if I put a whole bunch of sodium atoms into a container with a whole bunch of chlorine atoms, the chlorine atom only has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7 valence electrons. In order for that last octet, that last shell to be stable, it wants to have 8. And so what occurs in an ionic bonding is that this sodium here will give up that electron, that valence electron, to the chlorine. And so it transfers it over, as you can see in the diagram down below. There's that red valence electron that used to belong with the sodium, and now it has, the chlorine has taken up that electron, and now it is has become negatively charged. So it's an ion and has a negative charge because it has picked up a negative electron. And because this sodium here has lost its electron, it becomes more positive. So this is how we would write the symbol for sodium ion, would have a little +1. And this next diagram is just to show you, in the previous diagram I showed you one sodium atom ion bonding with one chlorine ion, and now here I'm showing you that you can have a 2-to-1 ratio. So here we have calcium, and there's its Bohr diagram. If you remember that term, Bohr diagram for its atom. And here are 2 chlorine molecules listed right here and here, and they are your Bohr diagrams for chlorine. Well, calcium just happens to have 2 valence electrons that it would like to get rid of, and the chlorine atoms would like to pick up one right here and one right here. So they form a nice bond together, but it is on a 2, looking over here, a 2-to-1 ratio. So there is 1 calcium here for every 2 chlorine here. And you can see that those are still signified by the positive and negatives to show that they are ions. So that was ionic bonding, transfer of electrons. So the next type of bonding is the covalent bonding. So covalent bondings, these atoms share, and there's in green again that key word. They share electrons. So I like to think of the covalent bonds or the atoms that form covalent bonds, they're nice because they like to share. Whereas the ionic bonds between a positive and a negative ion, they're not nice to each other. So this is usually between 2 nonmetals. So these are the ones that on your periodic table are found on the right side of your periodic table. So between 2 nonmetals, as you can see the hydrogen here, it looks different compared to our last one. There is a sharing of these 2 electrons that goes on here. So these 2 electrons share with each other. So there's a couple things I want to draw your attention to in this next slide. First off, I want to draw your attention to the electron model, which is using the Bohr diagrams shown here. Here's an electron model here, and here's an electron model. This one is for hydrogen gas, and this one down below is for the oxygen gas. So you can also see that there's a structural formula. So these are your structural formulas here for the bonding that occurs. So notice that when electrons are being shared in a covalent bond, this is signified by this line that you see. So I'm going to draw this line a little bit larger. So there's a line. It's a solid line that's shown between 2 symbols. And here's a shortened molecular formula to show you that there's 2 hydrogen molecules, 2 hydrogen atoms bonded together. So the next thing I want to draw your attention to is this down here. So this is showing 2 lines as compared to the one above. So these 2 lines, what that means is that there are actually 4 electrons being shared. If you could look back at the electron model, you can see here that there are 4 electrons that are being shared between the oxygen. So each line here represents the sharing of 2 electrons. And if there's only a single line, we call it a single covalent bond. So this is a sharing of 2 electrons. So share 2, and I'm just going to put a Li with a little dash to symbolize electron. And a double covalent bond, this means that we are sharing 4 electrons. Now there can be more, there can be triple covalent bonds, but typically what we are going to see in biology is the sharing of 2 electrons and the sharing of 4 electrons. And just as a reminder that would look like 2 solid lines between them. Now this is going to be different for when we talk a little bit later about hydrogen bonding, so I want to draw your attention to that now. So here's some more of those diagrams showing you chlorine atoms here, and when they form a bond together, because they're both nonmetals, they will share these 2 electrons that were in purple, and now I'm drawing over them in black. They will share 2 electrons, and you can see there's that single line that's showing you the sharing of 2 electrons. Again, the picture below, here's two nitrogen atoms, and when they form a bond together, because they want that stable octet on the outside, that they will end up sharing 6 electrons. And there's an example, the one example we might come across in terms of the triple bond. Now notice that these ones, this one here and this one here, they're symmetrical. So meaning that if I put up a mirror halfway in between them, I'd see a mirror image on both sides of these atoms. Whereas this one, water, and this is important, I'm going to come back to it later, water is not symmetrical. And so you can see here that, yes, water is made up of 2 hydrogens and 1 oxygen. And there's the diagram showing them sharing those electrons there. So we're going to come back to that because it's very important. We're going to talk about water in quite a bit of detail. So my first subcategory of covalent bonds are talking about this non-polar covalent bonds. So here's the definition underneath. This is where electrons are shared fairly equally between atoms. Now I want to explain what that means. So let's say I have these 2 electrons. I'm going to just make this one a little bit darker and green. I'm going to change up the color and make the other one blue. Okay, so here's my 2 electrons that are being shared between these 2 hydrogen ions. So I'm going to show you the path that this one blue electron will take. So it will circle around this hydrogen, and then it will come circle around this other hydrogen. And so it starts to make a figure 8, spending equal time around each atom. So now I'm going to come back to my other one, which I believe I made green. And the green one will do the same. So it's going to rotate around this hydrogen and then rotate around the next hydrogen and rotate it back around the first one. And so they spend equal amounts of time rotating around each hydrogen. So this is what I mean, they're shared equally. They spend equal amounts of time around each atom. And so this is typically because of symmetry. So I'm coming back to that symmetry again. So here I have the structural formula here for this hydrogen gas. So if I draw a line down the middle of it, I can see that there's it looks the same on both sides. It's symmetrical. The same can be said with methane. If I draw a line down there, you see a mirror image on both sides of the structural formula. Same here, mirror image on both sides of the structural formula. So these electrons will spend equal amounts of time around all of the atoms within the molecule. So the second subcategory of covalent bonds is this polar covalent bonds. So polar covalent bonds have an unequal sharing of electrons, which means there typically is a larger molecule that I like to say that molecule is a big pig because it hogs the electrons more than the other atoms within the molecule. So in this case, I've drawn water here, and you can see it's not a symmetrical molecule. So these electrons in this electron model here, these electrons are going to spend more time rotating around the oxygen, and then they'll go out to this one hydrogen, and then they'll come back and rotate around the oxygen a little more, and then they'll go once out to this hydrogen. So they spend more time because this oxygen is a big pig. It likes to keep those electrons more often than those hydrogens can actually hold on to those electrons. So what this is, it's a polar covalent bond. It's still sharing, but it's unequal sharing of electrons. This becomes really important when we talk about water because it's because of this unequal sharing that we end up getting these outstanding characteristics of water that is basis for life.